This lecture is going to continue our discussion about VSEPR theory, this time moving into where our central atom is also going to have lone pairs, and so our molecular and electron geometries won't be the same anymore. So we're going to go over a very brief review of our definitions. So we're going to go back over VSEPR, electron geometry, molecular geometry, and bond angle, just to refresh your memory in case it's been a minute since you watched the last one. And then we'll introduce the rest of the molecular geometries. This will involve identifying all of the molecular geometries based on both their steric and their coordination numbers. And then, of course, just like before, knowing all the bond angles. Now, there's something that you have to be able to do before moving on to this topic. So if you can't draw the Lewis structures for any given molecule, you're never going to be able to figure out its geometries. You have to know how many bonded atoms there are. You have to know how many lone pairs there are. So make sure you're not trying to go on to the homework or studying for this topic until you get that first. So a reminder to make sure you have your worksheet out in front of you. Each of the little boxes that we go over on the slides are going to be from the worksheet. So this just kind of condenses everything into one little nice formula for you. You don't even really need the PowerPoint slides if you have that. So now we're going to be covering all of the rest of the worksheet. So we covered that first column last time, and now we're going to be walking through, okay, for each steric number, what happens if you have one set of lone pairs? What happens if you have two sets of lone pairs, and so on and so forth. So just a reminder of what we're doing here, because this hasn't changed from the last video. Our basic idea is we have these negative electrons, and they're trying to repel each other. Our lone pairs and our bonds are both trying to repel each other, and our bond groups count as one little entity. So if you have a single, double, or triple bond, they're all going to count as one still. Now we're going to have something else that comes into play, and we mentioned it last time, but we didn't really talk about it. And that is that electron pairs show more repulsion than the bonds. This won't change the entire geometry. We don't have like a huge geometrical shift because of it, but it will shift the bond angles just a little bit. And so we'll talk about that on each box. So last time we talked about our 5 basic shapes. We're not really going to go over those again, except just in a very brief review on each slide to go over. So make sure if you need help with that, you go back to the last lecture. For our definitions, remember that our steric and coordination number are not the same necessarily. Last video, we only talked about the situations where they were. This video, the situations where they aren't are going to be more important. So let's just take NH3, it was one of the examples we went over. We had a steric number of 4 because we had 3 bonds and 1 lone pair. So that gave us a tetrahedral electron geometry. And now we know why it's tetrahedral. It has the 4 as a steric number. Its molecular geometry is different though, and that's because of its coordination number. Its coordination number is 3, and therefore it's not a molecular geometry of tetrahedral anymore. We need to look at, well, what does this look like if we don't see the electron pairs? The electron pair still changes the shape, but we don't see it in the nomenclature. So we'll learn about this, but it's called, this one is trigonal pyramidal, because the shape that just the molecule forms, just the bonded atoms form, is a trigonal pyramidal shape. And bond angle, same thing as last time, it's just your angle between your bonds. We don't talk about bond angles in regards to an angle between an electron pair and a bond. So that's really the only part of that can get confusing sometimes. We're going to skip steric number 2, and that's because if we have steric number 2 and we put a lone pair there, we don't have a geometry necessarily anymore. It's just a straight bond, and so there's nothing to talk about there. But we'll move on to steric number 3. So right now I put up what we already had from last time. We had our trigonal planar electron geometry, right? Because we separate everything out, which makes a triangle. It's all on one plane, and so we call it trigonal planar. We know what our bond angle is, not because we memorized it, but because we have a 360-degree circle divided in 3 parts, giving us 120 degrees each. Now what happens if instead of all 3 of those things being atoms, one of them is a lone pair? And so now we put a lone pair on that, and you can see, okay, that changes things a little bit. If we look at our electron geometry, that doesn't change. For a given steric number, your electron geometry stays the same, but the molecular geometry does. So we don't have all 3 atoms in a straight line because of the lone pair. So that's what I mean when I say the lone pair affects the geometry. If it was just 2 atoms, no lone pair, it'd be a straight line. But that's not our case. Let's think about what we would name this. It's not a straight line. It's like we took a straight line and we bent it. So it's called bent. Now let's look at our bond angle. We'd think by looking at it that it would be 120, right? We still have 360 degrees. It's still divided into 3 parts. So why wouldn't it be 120? And it is very close to 120. But that's where the part where we say the lone pairs take up more room comes in. Because the lone pair is going to squish it down just a little bit. And so it's going to be less than 120. You might say, okay, well, less than 120, but what is it? You can look it up for a given atom. All we really care is that you know that it's less than 120 because of the lone pair causing a little bit of a deviation. And we wouldn't ever ask you about the exact number because it just depends on the individual atoms. Now let's move on to steric number 4. So again, I have up what we did last time. What if we don't have any lone pairs? Remember, it's not on a plane. I'm going to just keep saying that over and over and over again because it tends to be the really common mistake made. It's in 3 dimensions. We call it tetrahedral based on the shape of the molecule. And this was the one that I said, you may want to memorize the bond angle. It's 109.5. It's a little bit tough to just see that by looking at it. You probably just need to know that one. Now let's go ahead and put some lone pairs on it. So we're going to start by just removing one of the atoms and instead putting a lone pair there. So I'll give you a second to look at it. Now, if you look at this shape and you think about what it looks like in 3 dimensions, again, maybe it's a good idea to have some toothpicks and candy out to kind of build these as we go along. You'll notice that when it's kind of in this sort of shape, you have a triangle base, but it's shaped like a pyramid now. It's a triangle base on a pyramid. Think about how we would name that. We have a trigonal pyramidal. Notice I'm going to start shortening all of my trigonals to just trig because I don't have a lot of room in the boxes. So trigonal pyramidal. The same thing happens with the bond angle here. It's still close to 109.5 because we still have 4 things that are requiring the shape to be in that direction. But the lone pairs are going to just shift down the bonds a little bit. And so it ends up being less than 109.5. Now let's just take one of these examples. Let's take NH3 because we've seen that a lot and I trust that you know what the Lewis structure looks like. You can see now why it's really, really important to be able to draw the Lewis structures. Because if I had just said, okay, what is the geometry of NH3, and you didn't first draw the Lewis structure out, you might not know that there's a lone pair there. And you'd get the wrong geometry because you didn't draw the Lewis structure right. So that's why you need to make sure you go back and do the Lewis structures really, really well before moving on to this. So continuing on with our boxes. Now let's take off another atom and put another lone pair there. So similar to the other ones, but an extra lone pair instead of an atom. Our electron geometry doesn't change. It's still tetrahedral. Our electron geometry is never going to change for a given steric number. Now let's look at our molecular geometry. This actually looks relatively familiar to the one we did on the last slide. It's not on a line, it's bent. And we still call it bent. But something that's important to notice here is that we got the name bent from 2 different steric numbers. And those aren't exactly the same shape even though they have the same name. So even though they're both called bent, when we discussed this on the last slide for steric number 3, the bond angles were 120. That was because we had a steric number of 3. Here we have a steric number of 4, and so our bond angles are less than 109.5 because it's coming off the tetrahedral geometry. Now notice that I also say less than AX3E. What does that mean? So the AX3 or the AXE nomenclature just helps us describe what's happening. So it means that the bond angle is a little bit less than the trigonal pyramidal bond angle too. The more lone pairs you have, the more it's going to squish the bond angles, the more the bond angles are going to shrink. So you don't need to know the exact numbers. I'm never going to ask you what's the exact bond angle of water, but I might ask you to say, okay, well, I'll give you CH4, which is, you you can see in the first box. I'm going to give you NH3, which you can see in the second box, or H2O. Rank them. Which one has the smallest bond angle? And you'd say, oh, well, water has the smallest bond angle because the electrons are taking up more room and are deviating the bond angle the most. So now let's do the same thing for steric number 5. I want to quickly refresh our memory on this one because this is the most complicated of the electron geometries. So I think it's good to kind of re-talk about this before moving on to what happens when we add the electron pairs. So this one, remember, we had two different types of electrons. Or two different types of electron groups. We had equatorial and we had axial. And I told you you could kind of picture this as two geometries stuck together, trigonal planar going through the center and then linear going up the top. Now, we called this trigonal bipyramidal because it's as if there's a pyramid here and a pyramid here, and they're stuck together at their base, which is a triangle. And we had two different bond angles. We had a 90-degree bond angle and we had a 120-degree bond angle. Our 120-degree bond angle was around our equatorial, and our 90-degree bond angle was along our axial. When we go to put in lone pairs here, we have to decide where those lone pairs go. Do we want to put them in an axial position, or do we want to put them in an equatorial position? And by we, I mean the universe. So we know that lone pairs take up more room than bonds. They want the most room, they take up the most space, they actually deviate the bond angles a little bit. So should we give them the most room possible or the least room possible? Most room, of course. So we want to put them on the angle that's the largest. Give them the most angle to work with. So we want to put them in the 120-degree area, which is the equatorial positions. So the electron pairs go in the equatorial positions so that they have the most room. Okay, let's look at this then. So we put this on here, and we can see that the lone pair goes in our equatorial spot, giving it a 120-degree angle about around there. Now let's think about what this looks like. If you wait till the equatorial spots are kind of on the bottom, you can see that it looks like a childhood playground toy. So you think seesaw, and that's the name of it. So it's a seesaw position. Again, always good to kind of take your toothpicks and candy, build it, and then you can definitely see the sort of seesaw-like aspect of it. Now let's look at our bond angles. We're going to have two again, just like before, where we had 90 based on the axial, and we had 120 based on the equatorial, and the same thing is going to happen here. And just like when we talked about steric number 3 and 4, the electron pairs are going to kind of misshape it a little bit. It's going to deviate the bond angle. It's going to shrink the bond angle because it's going to squish the bonds a little bit. So what happens if we add another one? Once again, we want to add our lone pairs to our equatorial positions because, again, we're giving it a 120-degree bond angle. So now we just end up with two of them in our equatorial spots. So sticking with our sort of elementary school flashbacks, we went out, we did recess, we played on the seesaw, we come back in, we learn our alphabet. So when this one shifts down like that, you can see it's in the shape of a T. And so we call this T-shaped. Again, you need to know both the names and the shapes, but you can see how highly related they are. So depending on your own learning style, you're probably going to learn one and use that to help you know the other one. Our bond angles for this, if you look at, we don't have a 120-degree bond angle anymore because we just have electrons there. And we don't typically discuss an angle between an electron pair and a bond. So our 120-degree bond isn't really in play anymore, but our 90-degree one is. And we still have the two lone pairs that are deviating the bonds, so it's still going to be less than 90. And of course, less than the situation where we had with the seesaw. So we can do this one more time. We can put another pair of electrons on this one. It still goes in an equatorial spot. And you can see now that all three of the equatorial spots are taken up by electron pairs. That gives us back a shape that's just in a straight line. It's different from the linear that we talked about with steric number 2, because when we talked about steric number 2, we didn't have any lone pairs. So it's a little bit different, but we still call it linear because the molecular shape is still in a straight line. Let's think about our bond angle here now. Before, when we discussed this bond angle, we said it was 90. But if you look at it now, we took away that bond. We just got rid of it and put an electron pair there. And so now we have a straight line. So our bond angle isn't going to be 90. It isn't going to be less than 90. It's going to be 180. Again, not something you need to memorize if you know the shapes, because you can just look at it and see. Now our last one, steric number 6. Remember, our nomenclature for this is octahedral, based on the three-dimensional shape that the atom, or that the molecule has. So even though it's a steric number 6, it forms an octahedron. And to think about what the shape of this one looks like, we're just thinking XYZ coordinate system, all on the ends of it. So all of our bond angles were 90. And this means that we don't have to worry about any situation where we have to worry about putting it on an equatorial or an axial or anything like that. All of the atoms are the same. So when we go to put a lone pair on, it doesn't make a difference where we put it. It's going to look the same no matter what happens. So if we do that now, we look at the shape, we see that we have a pyramid again, right? If you wait until the flat part is kind of rotated on the bottom, you can see that we have a pyramid. But the base of that pyramid is now a square, not a triangle. So we call it square pyramidal. The bond angles used to be 90, but now that lone pair is squishing all the bonds together a little bit, and so it ends up being less than 90. Now for our last one. When we go to put the lone pair on this one, it does matter. And that's because everything is 90 degrees. And so there's not an issue with, okay, let's give it the larger angle. But we don't want to put two electron pairs next to each other if we can avoid it. And you might say, well, we did that on steric number 5, and we did, but that was because it had a larger bond angle to work with. So even though we were putting them next to each other, they were going to be next to each other no matter what we did, so we had to give them the bond angle that was the largest. It's not the case with this one, though. We want to put it across from the lone pair so that it's exactly opposite. And so we get this shape. Think about this one and see if you can guess the name, even though we haven't talked about it. We have the shape that is a square, and it's not in a pyramid or anything of that. We just have a square shape all on one plane, and so we call that square planar. So now let's think about the bond angles. So far the pattern has been, oh, we added a lone pair, it ends up getting less. We add a lone pair, it ends up getting less. And that's because the more lone pairs we have, the more that they repel everything. But if we look at this one, and let's say we have our running it down this way. We have a lone pair over here pushing this direction. A lone pair over here pushing this direction. They're pushing in exactly opposite directions. And so the repulsion actually cancels each other out. And because of that, we're actually back to a bond angle of just 90. Not less than 90, just 90, because they're pushing in opposite directions. So in summary, we have our steric number, and that determines our electron geometry. This comes from spreading out all of the electron groups as far apart as possible, and we know that single, double, and triple bonds all count as one when we do this. We have these 5 basic shapes that everything else is built off from. Those start by forming our electron geometries. Of course, if our steric and coordination number is the same, or in other words, we don't have any lone pairs on the central element, then our electron and our molecular geometries are the same as well. All the molecular geometries that we discussed today are derived from the original electron geometry. In life, and whenever you're asked and people just say geometry, give me the geometry, they're always going to be talking about the molecular geometry. So make sure when you go through and study this, one, don't really start in on this homework too much until you first make sure you can draw the Lewis structures. Then make sure that you can both name it and picture it in your head. While I may not ask you to draw it, I may ask you to identify it, and you definitely need to know what it looks like to get some of the future topics.